Okay, in this video we're going to be looking at some past exam style questions on resistance specifically. So first of all, which graph shows a thermistor? So graphs A and B have got stuff about brightness and show resistance changing, so it's not going to be those. Graph C shows that as temperature increases, resistance decreases, which describes a thermistor, an NTC thermistor anyway. Whereas graph D shows that as temperature changes, resistance doesn't change, so it's definitely not that one. Okay, which circuit could be used to find the resistance of R? So to find resistance, we need the potential difference across R, which we'd need to measure using a voltmeter, and we need to know the current through R. So we'd need an ammeter in series with R. So A you don't have the ability to measure current, so that's not going to work. B, you don't have the ability to measure potential difference, so that's not going to work. C, you can measure current in series, potential difference in parallel, that looks pretty good. D, the voltmeter and ammeter are connected incorrectly, so that is not going to work. Okay, the meter in the circuit measures the potential difference across the resistor. Which unit is marked on the scale of the meter? Well, it's in parallel and we're measuring potential difference, so that's going to be a voltmeter measuring in volts. Okay, so two resistors are connected in a circuit as shown. What is the total resistance of the resistors? So you could use the equation and calculate this, that's fine. But I know that if you have two resistors in parallel, the resistance is always less than both of the resistors. So it's got to be less than 2. The list below contains the names of 5 different components that might be found in an electric circuit. Which of these has? So I'm just going to quickly describe each of the 5 and then we'll see what matches. So a capacitor is a way of storing charge used in things you want very high power from your storage. So like in Formula 1 cars use them quite a lot. LDRs, the resistance increases as light intensity decreases. Resistors, they turn electrical energy into thermal energy and decrease current. Thermistors, as temperature increases, their resistance decreases. And a variable resistor is a resistor that you can change its resistance of. So, a resistance that falls rapidly when temperature rises, we're talking about a thermistor. A resistance that changes when a sliding contact is moved, that is a variable resistor, also called a rheostat. High resistance in the dark, low resistance in daylight sounds an awful lot like an LDR to me. Okay, a lamp shines with full brightness when connected to a 12-volt battery as shown. So we've got a 12-volt EMF, 0.5 amps of current. Write down an equation linking PD, current and resistance. That's this one, V equals IR. The current in the lamp is 0.5 amps. Calculate its resistance. So we're going to rearrange this equation to make R the subject. Plug our values in, recognizing the PD across the lamp must be 12 because it's the only component in the circuit, giving us a resistance of 24 ohms. A resistor is now connected in series. So what's going to happen is the resistor and the lamp are now going to share the EMF of the battery. So state what happens to the current in the lamp. It's going to decrease. Why? Well, I'm going to use V equals IR to structure my explanation. Total resistance in the circuit has increased. Battery EMF is still exactly the same. So if resistance increases, current must decrease to give the same number. So just what change we might see in the lamp? Well, if there's a smaller current, we're supplying it with less power, it's going to get dimmer. Okay, so on the diagram, sketch a graph you'd expect to get if you plotted values of potential difference across a typical metallic conductor at constant temperature and the current through it. So if temperature is constant, its resistance is going to be constant, so we're going to get a graph that looks like this. How would you use the graph to find resistance? Well, this graph, the gradient will be potential difference divided by current, which using V equals IR is the resistance. So the gradient of this graph is the resistance. A laboratory technician wants to make a resistor of value 64 ohms using some resistance wire. He takes 1 meter of this wire and the wire is shown in the diagram. So the whole wire is A to C, but at the moment we're measuring across half of the length. He connects a crocodile clip at B, so it's half the length or 0.5 meters from A. We get a voltmeter reading and an ammeter reading. What is the resistance? Well, we're just going to use V equals IR again. We've got potential difference 12, we've got the current 1.5, so that's going to be 8 ohms. Okay, the technician now connects a crocodile clip to C, so we've now doubled the length of the wire, but the thickness is constant throughout. Write the readings you'd get ignoring the effects of the resistance of the ammeter, voltmeter or battery. So the voltmeter reading is going to be the same because it's got to be equal to the EMF of the battery. The current reading is going to be half because if we double the length of the wire, we double its resistance, so we must halve the current for the same EMF. Okay, so what is the resistance then? Well, the thing I'm going to use is resistance is directly proportional to length, as long as we keep the material and the cross-sectional area the same, which we have. So double the length, double the resistance. So it's going to be double what we got before, so it's going to be 16 ohms. Use your answer to B to answer the following questions. What is the resistance per meter of this wire? Well, this is the resistance of 1 meter, so that means the resistance per meter is 16 ohms per meter. What length of wire does the technician need for a 64 ohm resistor? So essentially, if each meter is 16 ohms and we want 64, we need to figure out how many sets of that we need, and that means we're going to need 4 sets of 16 or 4 meters of that wire for our resistor, and that completes our resistance pass exam solutions.